Welcome to the AI Research Roundup. I'm Alex, and today we're looking at a paper from the Hugging Face trending list, published on June 29, 2025, just 2 days ago. It introduces a new method for analyzing video that reduces GPU memory needs by nearly 4 times for high-resolution inputs. The paper is titled MEMFOF, High-Resolution Training for Memory-Efficient Multi-Frame Optical Flow Estimation. And as we'll see, this efficiency doesn't come at the cost of accuracy. In fact, it actually helps it. The authors tackle optical flow estimation, which is basically tracking how each pixel moves between video frames by combining a new multi-frame architecture with a unique high-resolution training strategy. Also, the authors share their implementation on GitHub. If you head over there, you'll find the complete source code, a set of pre-trained models, and even a demo notebook to get started. They also provide all the scripts you'd need for training and evaluation on the required datasets. On Hugging Face, 3 MEMFOF model checkpoints are available for download, along with usage examples. One is specifically trained for real-world footage, ready for you to try. Alright, this first figure really visualizes the core trade-off. On the left, we're looking at memory usage versus accuracy on the Spring benchmark. The vertical axis is the zero-shot 1-pixel error, which basically measures how many pixels are wrong by more than 1 pixel on a new dataset. So, lower is better. You can see MEMFOF in the bottom left, with the lowest error and the lowest memory usage. The chart on the right then shows the raw numbers for 1080p inputs. MEMFOF uses just 2.1 gigabytes, while others need 4 to 9 times more. So how do they actually achieve this efficiency? Well, this next diagram gives us a great overview of the architecture. On the left, it shows how the model looks at 3 frames at once, pulling out key visual details. It then builds a correlation volume, which is essentially a map of how pixels match up between frames to understand the movement. This information gets refined repeatedly to produce the final, accurate flow. The impact of this design is shown on the right, where another model needs almost 19 gigabytes for a 1080p video, while MEMFOF needs just over 2. Moving to the results, this table lays out the hard numbers from the Spring benchmark, comparing MEMFOF against other leading methods. We see a few key metrics here, like endpoint error, which is the average pixel distance error, and 1 pixel error, the percentage of pixels that are off by more than 1 pixel. For most of these, lower is better. Looking at the fine-tuned results at the bottom, MEMFOF gets the best scores across the board, all shown in bold. It's not just more memory efficient, it's also the most accurate. And that top-tier accuracy isn't just limited to the Spring benchmark. This table shows how MEMFOF stacks up on 2 other classic benchmarks, Cintel and Kitty15. The metrics here are similar. Endpoint error for Cintel and FL, all for Kitty15, both measuring prediction errors where, again, lower is better. Looking at the results, MEMFOF, right at the bottom, achieves the best scores on the Cintel clean version and for Kitty15. This really drives home that the model's high accuracy holds up across several different, challenging datasets. So to figure out why the model performs so well, the researchers ran an ablation study, basically testing different design choices one by one. This table shows the key results. They tweaked things like the correlation scale, the number of frames, and the update block dimension, which controls the complexity of the motion refinement. You can see the best result, highlighted here, uses 3 frames and includes a module called Global Motion Aggregation. This specific combination hits that sweet spot, achieving the lowest 1-pixel error while keeping memory use at just over 2 gigabytes. Building on that, this next table dives deeper into the training process itself. The researchers tested different configurations to see what worked best. They looked at things like using bidirectional flow, which means predicting motion both forwards and backwards in time, versus just unidirectional. They also compared training on original-sized images versus upscaled, higher-resolution ones. The results are pretty clear. The best setup, highlighted here, uses that bidirectional flow and trains on the full, upscaled images. This specific training strategy is a huge part of what makes the model so accurate. So to wrap things up on this paper, it's clear that these specific training decisions are crucial. The authors have effectively solved a major bottleneck in optical flow, which is the task of estimating how every single pixel moves between video frames. By combining a smart memory-saving architecture with a dedicated high-resolution training plan, They've created a model that is not only state-of-the-art in accuracy, but also practical for real-world, high-resolution video. That's all for this segment of the AI Research Roundup. Thanks for tuning in.